So today we shall discuss about current mirror. Now if you consider the name current mirror, as you know that mirror basically provides a reflection of the object. So likewise current mirror, as the name implies, it also provides a reflection of the current. That means given that you have some current source, you can reflect it at different places in the circuit. Now why do we really need this current mirror? If you consider a current source as implemented practically, it is basically implemented as some voltage source in series with some resistors, and which requires a considerable amount of space in the circuit. So in most cases we typically implement current mirror. We typically implement a single current source and then mirror it at different places of requirements in a circuit. So for example, if I consider a circuit like this, then when this current I is coming to this MOS transistor, we shall see that the same current I is also available over here, provided these two MOS transistors are geometrically identical. So let us consider this MOS transistor has a channel width of W1, channel length of L1, and this MOS transistor has a channel width of W2, channel length of L2, and let I in be the current entering the current mirror, and let this be the I out be the output current. So now as you can see that this transistor has got its drain and gate shorted, which means that this transistor will operate in the saturation region, but this transistor has to be biased in such a way that this transistor also operates in the saturation region. So assuming let us call this MOS transistor M2 in saturation, we have I out by I in equal to mu n COX W2 by L2 W2 by 2L2 VGS 2 minus VT2 whole square into 1 plus lambda VDS 2 by mu n COX W1 by 2L1 into VGS 1 minus VT1 whole square into 1 plus lambda VDS 1. Now we can see that VGS 2 equal to VGS 1. So we can write VGS 2 equal to VGS 1 and VT 2 equal to VT 1, because the technology for both these MOS transistors are same. So we can write VT 2 equal to VT 1, and also the mobility is constant, oxide capacitance is constant for a particular technology. So we have an opportunity of lot of cancellations. So we get I out by I in equal to, so mu COX, all these things cancels out, and we are left with W2 by L2. So this VGS 2 minus VT2 also cancels with VGS 1 minus VT1 whole square. So we are ultimately left with W2 by L2 into 1 plus lambda VDS 2 by W1 by L1 into 1 plus lambda VDS 1. Now if you ensure that VDS 2 equal to VDS 1, then this the numerator this 1 plus lambda VDS 2 and 1 plus lambda VDS 1, these two terms also cancel out. Otherwise since lambda is very small, you can ignore the effect of this term and you can make this approximately equal to W2 by L2 by W1 by L1. So the ratio of the currents in the two arms of the current mirror are same as the ratio of their aspect ratios. So Now I can, if you want to ensure that, now for a particular technology we typically keep L1 equal to L2. That means channel lengths are typically kept equal in a particular technology, which gives us I out by I in equal to W2 by W1 from this equation. Now, depending upon your requirements, you can choose W1 equal to W2 or scale up or down accordingly and get currents of required values in your circuit. So, we can write I out equal to W2 by W1 I in, which is basically the equation that guides us how to scale up or scale down the current from the output of a current source to provide current at different places of requirements in the circuit. This configuration particularly is very important because, as we shall see later in differential amplifiers, we popularly use a current mirror load to have a maximum gain, and in that case we typically use a current mirror load. Typically in most cases we use a PMOS current mirror load.